series, the integral test. Suppose a given function f is continuous, positive, and decreasing. F is continuous, positive, and decreasing on 1 through infinity. Then this series is convergent if and only if the corresponding improper integral, just writing 1 through infinity, is 1 through infinity. It can be any number through infinity, in fact. Positive number through infinity will have same. And that an is being named as the function f, if this is convergent. So this series and this improper integral behave the same. If this improper integral is convergent, then the series is convergent. And we've learned about this improper integral in previous section. At the same time, if this improper integral is divergent, that means when we evaluate this integral and it was infinity, the answer was d and e does not exist, or infinity, then the series is also divergent. Okay, and for the integral test, it is not necessary to start the series or the integral at n equals 1. So we can start from any number, but it has to be positive number like 2, 3, 4, 5, maybe 1000, etc. So let's recall from the improper integrals section. We saw that this improper integral 1 through infinity of 1 over xp, that is convergent. That means we get a finite number for this definite integral. If this is convergent if p is bigger than 1. If this power p is bigger than 1. So we can have only x, nothing else, just x raised to p, and if this p is bigger than 1, then this series is, this integral, this improper integral is convergent. If this p is less than equal to 1, then this improper integral is divergent. We saw that last time. Now based on this, we can work on this p series. Now we got a name for this series, 1 over n raised to p. Okay, it has to be n, nothing else like n minus 1, n minus 2. No, it has to be n raised to some number p, and some n from any number to infinity. This is convergent if p is bigger than 1. If this number happens to be bigger than 1, then this series is convergent. And this series is divergent if that number p is less than equal to 1. Okay, p series test. I mean, same thing, these two things are almost identical. Okay. In this case, n is 1, 2, 3, 4. We go into discrete numbers. Here 1 through infinity, in fact, it covers 1, 1.001, all the numbers, infinitely many numbers, in fact. Okay. So let's apply this p series test. Suppose we have a series 1 over n squared. Okay, p is 2 here. 1 over n root n. What is n root n? N root n is in fact n times root n, means n raised to 1/2. Now n raised to 1 and 1/2, so n raised to 1 plus 1/2, 3/2. So this is n raised to 3/2 and 1 over n 4, etc. are convergent because these 2, 3/2, 4 are bigger than 1. When the power p is bigger than 1, the series are convergent. In the same way, if we have 1 over n, so 1 over n means n raised to 1. 3 over root n, so 3 over root n means n raised to 1/2. And 1 over n raised to 1/5. All these powers are 1 or less. So these series are divergent. And we know the name for this one, we've seen a long time ago. This is called harmonic series. That's the most popular divergent series. Okay, now let's apply this integral test and check for this series for convergence and or divergence. Okay, so here sigma, and this term is always an is 1 over 1 plus n square. If you look at closely here for this integral test, now we need to write down a function based on this an. So then we take function is in terms of x, trying to make it continuous. It was discretely continuous, but we want to make everything. So we simply change n to x. So this is 1 over 1 plus x squared. Okay, and our domain is going from 1 through infinity. So 1 through infinity. Okay, 1 through infinity. Now we need to show three things for f. This f, look at here, to apply the integral test, we have to have f continuous, positive, and decreasing. Continuous, positive, and decreasing on the corresponding interval. So 1 over 1 plus x squared, if we graph, it will have a continuous graph. Okay, so the bottom is never 0. So this is continuous. So f is continuous. So that part is fine. Now next, positive. So we are taking x equals 1 through positive numbers. So 1 over 1 plus positive number square is always positive. In fact, this function, even if we take x negative, negative square is still positive. So this is always positive. So no question. F is positive for in this interval, for all x in this interval. And this function should be decreasing. Why? F is decreasing. So it's a little bit tricky to check. If you want to go through the full process, a function is decreasing when its derivative is less than 0. So derivative negative means the function is decreasing. So we were supposed to find the derivative. Okay, you can use the quotient rule. Find the derivative and show that the derivative is less than 0 on this interval. Okay, or if you, that one way, I mean that's the best way, but we might not have time to do this thing. So you can check the following. Since you have a graphing calculator, you can graph this function. I don't know the graph, but if you graph and look from 1 through all the way to infinity, here the function should be going slowly downward, slowly or fast, doesn't matter. It should decrease. Okay, you can check that one, that's the second. Or just think about the function. So 1 over 1 plus x squared, because the x is getting bigger and bigger. When x gets bigger and bigger, because 1 through infinity, so we are looking from 1 through all the way to infinity. When x is bigger and bigger numbers, that square is even bigger, plus 1 is bigger, and 1 over bigger means the fraction itself is smaller. When we divide a fixed number, in this case 1, a fixed number by bigger number, the fraction gets smaller, like 1 over 2 and 1 over 7. This is smaller than 1/2. When the bottom gets bigger, the fraction itself is smaller. So in this case, this is decreasing. Okay, I can just confirm. Bottom is getting bigger, the top is not changing anything, so this is decreasing. Okay, so now we are ready to apply the integral test. If one of these three conditions fails, we cannot apply. Okay, don't try the integral test. But a lot of times, I mean every single time, this thing will be granted. Okay, but you need to show. Now next, we want to find definite integral from here 1 through infinity, 1, because this is 1 through infinity. So we want to find this improper integral of function fx dx, which is in fact 1 through infinity of, the function is 1 over 1 plus x squared. Now this is 1 through infinity, so we cannot work on infinity, so we need to take a limit. Let's say 1 through infinity, let's put that as b, and let b go to infinity. 1 over 1 plus x squared dx. That is limit b going to infinity. Let's find the antiderivative of this. Okay, fraction, this is arctangent, by the way, tangent inverse x, and it goes from 1 through b. Okay, that is limit b going to infinity of, let's plug in upper limit, then lower limit. So this is tangent inverse b minus, then 1, tangent inverse 1. Okay, and let's put infinity as well. So this is tangent inverse infinity. What is that? We know that tangent pi over 2 is positive infinity from left, by the way. Tangent pi over 2 is infinity. So when we put infinity here, tangent inverse infinity, that is in fact pi over 2. Minus, there is no b, so no limit, tangent inverse 1. What is tangent inverse 1? Tangent pi over 4 is 1. That means tangent inverse 1 is pi over 4. Half pi minus quarter pi. So you had a half pi, you ate quarter pi. How much left? Quarter pi. So let's look at here. So when we had a series, then we convert that into a definite integral. And we know that if this definite integral is convergent, the series is convergent. If the this improper integral is divergent, then the series is divergent. And we just found this improper integral to be convergent because this number is a finite number. So then the series is convergent because this improper integral is convergent. The series is convergent because the improper integral is convergent. Integral convergent means it's got a finite number. Okay. In fact, this test is not easy, the integral test, because you have to test these three things. When you have a terms an, you convert into a function, then need to check three things: continuity, positivity, and decreaseness. Okay, so it's kind of a long process, but this one is good because you can, as soon as you know how to find the antiderivative or this improper integral, then you can check whether the series is convergent or divergent at the same time. So it involves a lot of work because here is an definite, this improper integral. So I would leave this for last resort unless the question asks to use integral test. Okay, generally they'll ask you to use integral test, then you don't have any other options. But if you are testing a series, if whether a series is convergent or divergent, leave this for last resort. Do not try to use this. But if all other tests fail, then use this. Okay, this one, it really works, but you need to satisfy a lot of conditions. And see website for more examples.